All right. Thanks everyone for coming to today's Wenyu's PhD defense. So I'll just quickly introduce Wenyu. So he joined NYU and started working with me since fall 2019, before COVID. And this is this semester is the end of his 5th year. And Wenyu has been working with us on various topics. At the beginning, we were trying to figure out what are the appropriate research topics. So we tested something like generative modeling, and then eventually both generative modeling and representation learning for robotics and automation in general. So you will hear his presentation today on two major different application areas. So without further ado, I will give the floor to Wenyu, and you have about an hour to present your defense to the committee members. And in between, I think we welcome any kinds of questions, as long as they're not like, if you want to ask some questions that are quick to answer, like a clarification type of questions, feel free to unmute yourself and interrupt and ask Wenyu to clarify. But if the question is a bit too long, that requires more iterations of Q&A, I would suggest we leave those questions towards the end to keep the continuity of the presentation. Yeah, if everybody agree with that, I think we should we should start. When you can start sharing screen.
Okay, sure, no problem. Let me share my screen. And
just before we start, Chen, I put in text also. I have a sharp stop at 2:55, so I think we have enough time just to let everybody know that's a panel I need to go for. Yeah, I appreciate it.
Yeah, no worries. I hope we don't need to. Hopefully we can end a bit earlier. Yeah, but thanks for letting us know. Yeah.
Sure.
Also, can everyone see my screen? Yeah, so I will start. Wait one more. Okay. So thank you everyone for being here. I'm glad to share my research, deeper representation learning on spatial and temporal data towards design and construction automation. And first, it is a brief self-introduction. And currently, I'm a 5th-year PhD candidate in Mechanical Engineering Department, directed by Professor Chen Feng. And I got my master's degree in Mechanical Engineering as well in Northwestern University, and a bachelor degree in Engineering Mechanics in Dalian University of Technology in China. And my research interests are computer vision, robotics, generative AI, and reinforcement learning. And here is a list of publications I have, and I will use 4 of them for this dissertation. And here is the outline I will follow for this presentation. First, I will give you some background knowledge of my works, and then I will mainly talk about 2 research questions in design and construction automation. And finally, I will I will give you the conclusions and the future works. And in my thesis, I study how to enable AI and robotics in 2 important engineering processes. The first is design automation. The second is construction automation. Design is a process to create a description of new facilities, usually represented as the detailed plans. And the construction is the following process to make the design into reality. And so in my thesis, I will study 2 research questions in design and construction automation. And for the design automation, the generative content by the current method are often limited to rasterized format, such as images. And however, in construction and manufacturing industries, objects such as CAD models and the city layouts are often represented in the vectorized format, such as polygons or the geometric primitives. So this leads to my first research question: is how to generate large-scale vectorized data by deep generative modeling. And for the construction automation, the current mobile robots are able to free humans from dangerous working sites and heavy workload. However, how to strategically manipulate the environment is still challenging for the current construction automation. So this leads to my second research question is how could autonomous mobile robots accurately change the surrounding environment? And after a long period of investigation, we found that learning a good representation could potentially solve these two research questions. Specifically, for the first research question, we think that we can map the complex statistic of large-scale vectorized data in latent code by using the deep representation learning techniques. And then this learned representations is able to generate the novel content. And for the second research question, and we can explicitly estimate the state by learning on a temporal series of observations perceived by the agent. And this estimated state could enable mobile construction robot to learn effective policies for the accurate environment manipulation. And so this is an overview of this dissertation. For each research question, I will introduce two works for discussing how deep representation learning techniques can solve this problem in detail. So in the first part, I will introduce a work which aims to learn hidden representations through deep autoencoder for the large-scale city layout generation. And in the engineering domains, the objects we encountered are often in vectorized format, but there is a lack of such method that can generate vectorized data over a large scale of a spatial area. And the recent method, such as polygene, can only generate a single vectorized object. However, there are two difficulties that prevent the generative models to be applied for the large-scale vectorized data generation task. The first challenge is the lack of a public large-scale dataset, and the current vectorized dataset is restricted at a single object level. The second challenge is the difficulty in modeling the complex statistic of large-scale vectorized data. And currently, people still rely on some rule-based method or the software such as the city engine to model large cities. And some existing work for vectorized data generation can be divided into data-driven and non-data-driven method. And for the data-driven method, the most recent work for such as the polygene can generate a single vectorized data. And the most relevant work, NTG represents the city road layouts as graphs, but this method only considers the 2D generation without considering any 3D characteristic of real cities. And by contrast, the most widely used method for large-scale data generation are non-data driven, such as the procedure generation method. And this method requires the human expert to input design parameters. And the city engine also requires a human input. And this non-data driven method are away from the motivation of design automation, which aims to reduce the human involvement in the design process. Since there is a lack of a large-scale public dataset, we propose our dataset, a Real City 3D, which is a large-scale data repository of real-world city models. And our dataset contains a set of georeferenced 3D primitives, and each one is represented as the semantic labeled polygon mesh. And our Real City 3D dataset is collected from multiple big cities like New York and Zurich. And our dataset supports the three different types of 3D data, including meshes, point clouds, and voxels. And for reducing the generation complexity, we simplify the building primitives in the raw data from LOD2 to a simple bounding box. Therefore, a block of building layouts will be represented as a set of 3D boxes. And here we also consider the 2D box set by ignoring the z dimension from 3D. Therefore, each building layout it will be represented as the 6D point. And here the XY denotes the coordinate of the center point, and the LWH is the length, width, and height of the box, and the A is the rotation angle. And then in order to preserve the spatial relationship among the buildings, we organize the box set hierarchically in a tree, specifically as shown in the figure, and we will the closest two boxes such as box 0 and box 1 will at level 0 will be treated as a children node, and then they will be merged to generate their parent node in the level 0. And here is a box 2. So similarly, all the boxes will be merged hierarchically from left to right until the parent box becomes a root node. And so in this way, a box set will be organized in a tree. Regarding the tree structured data, we propose a tree structured autoencoder for the layout generation. Specifically, in the encoding process, the encoder is learned to extract and merge the geometric parameter and the feature vector of each children box to generate their parent box from level 0 to the root level. And this encoding process will end until reaching the root level, and then we will have a root feature which is expected to contain all the information of the box set. And for the decoding process, a decoder learns to decode from the root features to the leaf level. And it should be noted that in the decoding process, besides to predict the geometric parameter and the feature vector of each box, and it should also predict whether this box is a leaf node or not. And so here we use another L to denote such a binary vector to indicate whether the current node should be further decoded or not. And for the loss function, it is the summation of two losses. The first loss is the L1 loss between the predicted geometric parameter and the ground truth geometric parameter of each box. And the second loss is the binary cross entropy loss between the ground truth and predicted binary indicator. And in the experiment section, we first compare two different feature extraction functions, LSTM and MLP. And for evaluating the result, we treat each box as the four-corner point, so the box set will be treated as a point cloud. And for the evaluation matrix, we include the transfer distance and the earth mover distance. And we also design another metric called OAR, the overlapping area ratio. This metric measures how much the overlapped area in the generated set. So because we do not want the boxes overlap with others in the generated set, similarly in the real world, the building layout do not overlap with others. So this OAR metric will be the smaller, the better. And here are the quantitative results of this experiment. And from the table, we can see that the LSTM-based feature extraction functions outperform the MLP-based function among all the metrics. This reveals that this recurrent network, such as LSTM, is necessary for addressing the long-term dependency of this hierarchical structured model. And we compare our AE tree model with multiple data-driven method. We include the sketch-RNN, PointNet, and PointNet++. And for the evaluation matrix, we include the four matrices, the GSD, COV, MMD, and OAR. And from the table, we can see that our AE tree model outperform other baselines regarding each metric. And here I will show some reconstruction results on both the 2D and the 3D. And we also conduct a latent code interpolation experiment. Given two samples of S and T, we can get the intermediate result by applying the decoder to the linear interpolation between these two latent codes. And this result demonstrates that the smoothness of our latent space. And this reveals that our latent representation are generative instead of simply memorizing the training set. And and here are some generation results. We compare our method with multiple data-driven method, and we also include one non-data-driven method, city engine, as the upper bound. And from this image, we can see that our A-tree model can produce a higher quality city layout than the baseline method. And our method can also achieve 3D generation. And then we will see how the learned representations can be used for one urban planning application. Specifically, we use the A-trace encoder to encode the 45,000 Manhattan's urban layout to latent representations. And then we use a Gaussian mixture model to cluster this 45,000 latent representations into 11 clusters. And from this table B, we can see that each cluster has a different level of density and evenness. And from this bar chart, we can see that the Manhattan's urban layout has a high percentage of cluster 8 and cluster 10. This characterizes the moderate density and the even green, which are emblematic patterns of Manhattan city. And by using this Manhattan's urban layout composition as a baseline, we can characterize the neighborhood urban layout composition. And this bar chart shows, and here we examine two towns, the Stuyvesant Town Cooper Village and Upper West Side. And from this bar chart, we can see that this town is departure from the general pattern of Manhattan city with a larger deviation. And the Upper West Side resembles the general pattern of Manhattan city with relatively small deviation. And these two images verify this result. From the left image, we can see that the Stuyvesant Town Cooper Village contains a set of small buildings which are away from the general features of Manhattan city, while the Upper West Side is quite similar as the Manhattan. And here are some takeaways of this work. First, existing works are restricted to generate a single vectorized data. Second, there is a lack of large-scale vectorized data set. Third, the A-tree can effectively capture the complex geometry of large-scale urban layouts through deep representation learning. Fourth, generation scale is still limited in current work. And fourth, the A-tree still need the data preprocessing to organize the box set into a tree. Although the A-tree can generate the city layout in a data-driven fashion, it still requires the data preprocessing. Therefore, in order to avoid any manually data preprocessing, we propose another transformer-based method for the city layout generation. And for the general layout generation task, leading approaches always represent the layout as a sequence of elements and use transformer-based methods to model the data distribution. However, this method always require predefined orders due to the nature of transformer-based method. Because the transformer needs the positional embeddings. But such predefined order will add additional design effort and may introduce undesired constraints and often not feasible in some applications such as layout completion. So the question is that, can we eliminate this constraint? So for addressing this problem, we designed our method called CityGPT, and our method has two stages. In the stage one, we firstly will mask out some building layout from the raw data, and then this masked input will be fed into this transformer embedder to get embeddings, and then this embeddings will together with the positional embedding to feed into this transformer encoder to get the latent tokens. And here we use the petrify operation to downsample a sequence of tokens to a sequence of patches. And then these patches will feed into a transformer decoder to predict a positional map. And this positional map represents the probability of each building that occupies a certain position in the design area. And in the second stage, we feed the same masked input to the encoder, and this encoder shares the same structure as the encoder used in the first stage, and then we will get the same same tokens, and then we will sample some positions from the positional maps in the first stage to and which will be served as the positional embeddings for the masked tokens. And for the unmasked data, we will use the mean centers as the positional embedding. And then this all information will feed into the transformer decoder to predict the representations. And finally, each of these predicted representations will feed into an autoregression model to generate the building layout. And since the positional maps can serve as the positional embeddings for the second stage, our model does not require any predefined order to generate the whole city layout. And here we compare our city GPT with multiple baselines, including SketchRN, Layout VAE, Layout Transform, AE Tree, and Layout DM. And we include the three evaluation matrix, the CitySim, which measures the similarity of two city layouts, and FID is pixel level distance, and the persistent distance. And here are the quantitative results. From this table, we can see that our method outperforms the baselines among these three persistent distance and as well as the CitySim metric. And for the FID metric, we can see that with the additional predefined order as an input, the layout transform slightly outperform our method. And here I will show some qualitative results. And from this image, we can see that our method can generate a higher quality building layout, city layout than the baselines. And with additional predefined order as an input, the layout transform can also produce the comparable result. And we also conduct two application studies to verify our model design in the stage one. And we change the transformer decoder to MLP, and we also remove the petrify operations. And here are the results. From the table and the images, we can see that these two key operations in the CityGPT are necessary and important to achieving the best performance. And finally, I will show some interesting applications of our method. First, our method can achieve an infinity generation. And from the figure, we can see that starting from a small set of building layouts, which are illustrated as this purple color, and our method can generate the city building layout in a large scale. And the second application is the city complementation. And from the figure, we can see that if we remove a region of building layouts, our model can fill this empty area with novel content by referring the surrounding layout. And our method can also achieve conditional generation. This figure shows that our method can generate a city layout conditioned on the road networks. And our method can also generate LOD1 3D models. And here are some takeaways of the first of this work. First, the most existing works rely on predefined order. And the second, the proposed two-stage method really eliminates this constraint. Third, our method can achieve infinity scale generation, city complementation, and conditional generation. And so for now, I have answered the first research question, how to generate vectorized data over large scale spatial area through deep generative modeling by the proposed two works. And in the design phase, then we will move to the next phase of engineering process, the construction, which aims to make the design into reality. In this part, I will also introduce two works to answer the research question, how could autonomous mobile robots accurately change the surrounding environment? And the first work will study this research question in a simplified grid world. And the mobile construction robots faces the challenge of accurately building structures while navigating in a dynamic environment when the GPS is not accessible. And we call this task as a mobile construction. And in nature, many biological organisms can complete a mobile construction task. We see this behavior, for example, with the mound-building termites can build complex structures. And this activity requires the good coordination of localization, mapping, and planning. So here is the question that can we create a robotic system that can complete a mobile construction task? The robot typically relies on the SLAM to navigate when GPS is not accessible. However, a mobile construction task breaks the static environment assumption due to the actively changing the environment. And the challenge of mobile construction task is illustrated in this cartoon. A robot aims to build a structure of stacked cubes, as shown in the figure A. And without GPS, the agent navigate itself by in this evolving environment by observing the build structure. However, if planned poorly, this agent will build similar structures as shown in the figure C, and these same structures will confuse its current localization. And therefore, ignoring the localization and the construction planning will lead to poor construction qualities, as shown in the figure D. So in conclude, the localization and the construction planning are interdependent in mobile construction task. And the most of object rearrangement tasks do not involve any navigation because they use the static manipulators to rearrange objects in a tabletop. And the most relevant mobile rearrangement task always assume knowing the ground truth positions of the agent, which are not true in the mobile construction task. And some visual navigation tasks only focus on navigate the agent in an unseen environment without manipulating or modifying the environment. So in conclude, all these related work solve one aspect of the interdependent challenge. So in this thesis, I aim to solve this interdependent challenge in one shot. So for effectively starting the proposed mobile construction task, we create a simplified grid world environment from 1D to 3D. Although simplified, such grid world environment allow us to focus on studying the agent's ability to coordinate the localization and the long-term planning in a dynamic scene. And the bottom image shows the real-world samples of each task from 1D to 3D. And here I will use the 2D simulators to explain our task definition. In the 2D, the agent will move in the X1 plane to draw these green circles as a target design. And at each time step, the agent can only observe a 5x5 grid or a 5x5 square region of the world. This will make our mobile construction task a partial observable problem. And the agent will either move along the one direction of this with the stochastic distance functions, or break one or laying one break at its current locations. We visualize the correctness of the construction action using the different colors. And in this task, the agent needs to plan its actions to maximizing the yellow pixels while minimizing the red pixels for the best construction performance. And in our mobile construction tasks support different various environments from 1D to 3D, and we also have diverse type of design targeted designs. And for solving this task, we test different types of method. And we include a family of deep reinforcement learning methods such as DQN, DRQN, and PPO. We also include a handcrafted SLAM-based policy and a search-based policy, which combines the DQN with Monte Carlo tree search. And we also collect the human data. And for collecting this human data, we create a GUI game which shares the same configuration as the simulator played by the other baselines. And a simple baseline of our mobile construction task is a vanilla DRQN policies, which uses the recurrent network with the raw observations as input to plan its actions. After testing this baseline method, we found that most of them perform poorly on the proposal task. We believe that the low performance is due to the difficulty in learning meaningful representations and effective policies jointly through reinforcement learning. Therefore, we propose our method, which decouples the representation learning from reinforcement learning. Specifically, we will pre-train a localization model to estimate the positions of the agent at each time step. And then these estimated positions will, together with the targeted design, will feed into the policy network to plan its actions. Because our policy network is a recurrent network, we only need to repeat the same process to make a sequence of actions. And here I show the quantitative result of this work. And the dark green color showcase the result of our method, and the other colors are the baseline method. And from this bar chart, we can see that our method outperforms the baselines among most of the tasks. And we can also see that the performance of each method decreases as the task dimension increases. This reveals the increasing difficulty from 1D to 3D. And here are some qualitative results of a vanilla DRQN baseline and our method. From these images, we can see that our method outperforms the baselines among all the tasks. Especially in the 3D, the vanilla DRQN failed to construct anything, while our method can construct reasonable structures. And in our work, we also identify 4 potential challenges exist in the mobile construction task. And the first is the lack of localization information. The second is the uncertainty exists in the transition functions. And the third is the lack of landmarks in the initial environment. And the fourth is the obstacles in the 3D environment. Here I use the DRQN result as a baseline performance. And from the figure A and the figure B, we can see that by adding the ground truth positions into the policy or remove the uncertainty from transition functions, the performance increase compared to the baseline performance. And from figure C and D, we can see that by adding some landmarks in the initial environments, which are illustrated as this red pixel, and our agent can solve this problem perfectly. This reveals that the lack of landmarks in the initial environment is a big challenge of mobile construction task. And lastly, we can see that by removing the obstacle from the 3D environment, the performance increases. This reveals that the abstraction is another challenge in the 3D task. And here are some takeaways of the first of this project. First, the major challenge of mobile construction task is the interdependence between the localization and the long-term construction planning. And the second, the existing deep reinforcement learning method perform poorly on the proposed task. Third, the decoupling localization modules from reinforcement learning is a promising way to solve the interdependent challenge. Fourth, the grid world environment is simplified yet non-trivial for the current methods. So the snacks studies this interdependent challenge in a simplified grid world where the complex sensing models of the agent is ignored. This makes it away from the real-world setups. Therefore, I study a similar challenge in another environment manipulation task called mobile object rearrangement in a continuous environment. The definition of mobile object rearrangement task is that the agent to recover the goal state from initial state by manipulating multiple objects without perfect localization. In the mobile object rearrangement task, manipulating objects will significantly change the surrounding environment, and it will break the static environment assumption of a SLAM. So in the mobile this mobile object rearrangement has the similar interdependent challenge between the localization and the manipulation planning. And the existing work for object rearrangement works also always assume knowing the ground truth localizations. For example, in the visual room rearrangement work, it assumes knowing the global positions of the agent. And for the multi-steel mobile manipulation work, it assumes knowing the relative pose from the agent to the target objects. And meanwhile, the habitat tool only manipulates a tiny object such as a small cup in the table. On the table will not change the scene, will not change the environment significantly. In other words, the scene of this task can still be treated as a static. This will make the SLAM-based method easy to be used in the habitat tool task. And these two factors will make the existing object rearrangement task different from our mobile object rearrangement task. And the goal of our mobile rearrangement task is to let a mobile robot to rearrange all the objects to the target locations without knowing the GPS. The agent can only perceive the first-person images as an input, and the top-down view is not accessible. And the agent needs to plan its actions from move forward, turn left, turn right, and pick or drop objects. And in this research work, we decouple the mobile rearrangement task into two subtasks, the pick and drop task. And in the pick task, the agent is required to pick an object randomly placed in the environment. In the drop task, the agent needs to drop one object to the target locations. Therefore, the completion of the rearrangement task is achieved by successfully completing a sequence of the pick and drop subtasks. And for solving this problem, we designed similar pipelines as used in the mobile construction task. And this pipeline has two major components, the LNet and the policy net. The LNet is for estimating the agents and object positions by using the first-person images as input. And here we also estimate the pose uncertainties, which are represented as which are approximated using the 2D Gaussians. These uncertainties are illustrated as the colorful contours shows in the image. And then these estimated poses together with their corresponding uncertainties will feed into the policy network. And to acknowledge the decomposed subtasks, we decompose our policy networks into two primitive policies, the drop policy and the peak policy, for solving each subtask individually. And a decision policy will execute a high-level command to take a sequence of these primitive actions in order to finish this rearrangement task. And in our pipeline, the LNet is trained through the supervised training, and all the primitive policies will trained through the reinforcement learning. And here in the experiment section, we compare our method with multiple ResNet baselines. Here, the plus image means that it is the end-to-end policy with only first-person images as input. And the plus delta pose means that we add additional delta pose to the policy network. And the plus landmarks means that we give the agent a reference to identify where to place the objects. And here we include the three metrics for evaluating the results. And for the success metric, if the agent successfully rearrange all the objects to the target locations, this value will be 1, otherwise it will be 0. And the fixed strict matrix measures a percentage of correctly rearranged objects to the total number of objects. And for the energy remaining matrix, we design the energy as the distance between of each object between its current locations to the target locations. So this metric will be the smaller the better. And here are the quantitative results. From the table, we can see that our method outperforms the baselines among all the metrics in the rearrangement task and the peak task. And it should be noted that by adding additional relative pose to the policy, the baselines slightly outperform our method. But this additional improvement thanks to the relative pose as an input, which are not used by our method. And for the evidence study, we compare we conduct this evidence study to verify the usefulness of uncertainties. From the table, we can see that with the uncertainty as the input, the policies outperforms the policies without uncertainty as the input among all the metrics. This proves that the effectiveness using the uncertainty as a part of the input to the policies. And here are some takeaways of this work. First, the decoupling or localization network from policies outperform end-to-end policy on the MOR task. Second, integrating the uncertainty into a policy achieves better performance than uncertainty unknown policies. And so to conclude, in this thesis, I present two data-driven methods, which learns the hidden representations on the larger scale vectorized dataset, aiming to automatically design city layouts. And I also proposed two methods which are decoupling representation learning from policy learning and integrating the uncertainties into the policy. And these two methods are potential to enable mobile robot to manipulate the environment with motion and environmental uncertainties without need of perfect localization. And here are some future works of of this thesis. For the design automation, the current CTGPT and AE3 can only generate buildings in the LOD1, so the future work could extend to LOD2. And the current work can only generate building layouts. Therefore, automatically generating cities with more elements such as road or rivers could be another potential direction. And for the construction automation, first, the complex environmental dynamics and the detailed manipulator control are ignored in the current works. So these factors could be included in the future works. Second, studying this interdependent challenge in a more realistic scene would be easier to transfer the policy to the real world. And finally, many thanks to my advisor and the committee members, collaborators, lab mates, and my family. I would like to thank my professor, Feng. He gave me a lot of valuable suggestions and guidance on my research and my personal life as well. He taught me how to find interesting research questions and how to think about solutions and many other important skills for being a good researcher. I would also want to thank my community members, Professor Ludwig, Professor Farog, Professor L'Oreal to join in my committee, and they gave me a lot of constructive comments and suggestions to improve my thesis. And I also want to thank my collaborators, Cong Cong, Siyuan, Ruoyu, Rongjing, Ruixuan, and many others. Without their help, these works cannot be accomplished. And I also want to thank my lab mates. I spent a wonderful 5 years with them, and I also learned a lot from this creative group. And last but not least, I want to thank my parents and my fiancé for their love and support during this challenging journey. And that's pretty much I want to share for this presentation, and I'm open to questions. Thank you.
Okay.
Yes.
Thanks, Wenyu, and I think we're open to questions. We have some. Typically, we start from like the public. I think now the public audience here is really just 2 PhD students in my group. So I don't know. Let me stop recording first. Let me